Welcome back, guys. We're going to talk about Chapter 5 and Newton's third law of motion. You ever heard the phrase, for every action, there's a reaction? That has roots in Newton's third law. To understand what's a reaction and what's a reaction, we need to understand what forces are at work and what an interaction actually is. Alright, an interaction occurs between two objects. Alright, it requires a pair of forces acting on the two objects. Alright, so you have one object A pushing on object B. Well, object B is going to push right back on object A. Alright, one force will be the action that initiates this interaction. The other force is the reaction. This interaction and these forces together can cause an effect on one of the objects or on both of them. Alright, so I've got a couple of examples here for you. A baseball strikes a bat, the baseball goes flying into the field. Right, the objects at work are the bat and the baseball. The action force is the baseball pushes on the bat. The reaction force is the bat pushes back. Sorry, that's supposed to be on the ball. What's the effect? Well, the baseball goes flying. Okay, I've got another example there with a picture for you. Alright, continuing on. Sometimes it's not so easy to identify which is which. Alright, for example, we got Fred here. He's leaning against the wall. Well, what two forces are at play? What two objects are at work? Well, the objects would be Fred and the wall. What's the action? Well, Fred pushes on the wall. Reaction, the wall pushes back on Fred. Alright, this also satisfies Newton's first law. Forces equal out. You have equilibrium. Nobody's moving. Alright. Now, understanding those interactions and those action-reaction forces will help you understand Newton's third law a little better. So, in Newton's words, whenever one object exerts a force on a second object, the second object will exert an equal and opposite force on the first, right? Direction is key. Remember, forces are vectors, so the direction matters. Okay, it's very important not to confuse the forces with the effects of the force. Alright? So, for example, here we got a high-speed bus colliding head-on with a bug. Now, they both experience the exact same force, right? Equal in magnitude, opposite in direction, right? But the poor bug has a very different effect from feeling this force, right? He, unfortunately, splatters all over the windshield, right? Where the bus has no effect, it feels nothing, just has to clean the window, right? The forces are the same, but the result or the effect of the forces is very different, right? So don't get those two confused. Now we know from previous chapters that acceleration equals the net force divided by the mass. Alright, therefore we know if the same net force applied to a small object and to a large object, then their acceleration will be very different. Because we know that acceleration is inversely proportional to that mass. Okay? So remember in that, we can use that to help us with the third law. So for example, we have a cannon fired. Okay? Now the same force acts on the cannon as on the cannonball that's inside the barrel. Their accelerations will be very different because their masses are very different. Right? So the cannon, you got this big bulky cannon, right? So big mass will get you a little acceleration when using the same force, right? So little acceleration, big mass. Now the cannonball has a little mass, big acceleration, right? Okay, video of a similar situation, all right, that you can watch there. And some extra credit work and thrown in the mix. All right, now we've talked about the support force before. Right, here's Nellie again. If she's on flat ground on her snowboard, her normal force, aka support force, and her weight balance out, right? She doesn't go anywhere. But you put her on an incline and then look what happens. Balance no longer, and she will start accelerating down the hill. Alright? Another view of something similar. Here you can see as the degree of incline increases, so does how that normal force balances out the weight until, look, normal force no longer, zoop, ice falls down the wall. Alright? Now, how do we deal with vectors that are at angles to each other? Right? From previous chapters we know if vectors are acting in the same direction, you can just add them up. If they're acting in opposite directions, well, you can subtract them. But what do you do if they are at right angles to each other as shown here in the picture? Right? We've got this airplane 80 kilometers north, has a velocity 80 kilometers north. It's hit with a crosswind going 60 kilometers per hour to the east. Right? Well, that's going to affect the plane, right? The effect's going to be the plane no longer can fly in a straight line, but it's going to fly in this diagonal here. Well, how can we figure out the magnitude, the new velocity? Well, you're going to have to use something called Pythagorean's theorem that you may remember from math class. It was used to find the hypotenuse of a triangle. Alright, so here's how it goes. To find the resultant, or the sum of those two vectors, have the x horizontal piece squared plus the y vertical piece squared. Add them together, take the square root. So let's see if that works with our plane. So 80 squared plus 60 squared gives you 10,000. You square root the 10,000, and there you get your 100. Alright? That's what you do if vectors are acting at angles instead of in straight lines. So this is just a summary of the 3 laws with a couple of videos to help you understand things a little better. Alright, as always, if you have any questions, contact me, talk to a friend. Make sure you watch your videos, read your book. Alright, feel free to post in the Muddiest Points forum. I will also be able to help you there. And good luck.